We learned how to evaluate improper integrals where one of the bounds were either positive or negative infinity. Let's look at the other type of improper integral, specifically where one of our bounds could be where there is a vertical asymptote or there is a vertical asymptote somewhere within the bounds of our integration. So the work around this here is really just to use one-sided limits. So let's take a look at this particular example here. We've got the integral of 1 over x minus 2. And so if we're looking at 1 over x minus 2 and we're integrating this from 2 to 5, let's think about what this is saying here. We're effectively trying to find the area underneath this curve from 2 all the way to 5. Now the problem here with this is that we have a vertical asymptote here at 2. So analytically, if we're trying to evaluate this integral, I'm going to get something that's going to produce something that is undefined. However, if we can really just think about this area underneath this curve and finding a one-sided limit, if, in other words, finding the area underneath this curve as we get really, really, really close to 2 using one-sided limits, then we've got our strategy or we've got our approach. So I'm going to write that one-sided limits. That is our ticket. And let's take a look at setting up this improper integral here. So we, again, are going to first establish that we have a vertical asymptote at x is equal to 2. And we're now going to write this limit statement now as the following. We're going to say, let's find the limit. Again, we're using a as the limit as a approaches 2. And from which direction are we approaching that 2? We're approaching that 2 from the right side. And again, I'm choosing 2 because that is where our vertical asymptote is. So we want to find the area underneath this curve as a approaches 2 from the right side. And so then I can write that integral as a again, 5, 1 over root x minus 2 dx. So again, we're replacing the bound where there is a vertical asymptote and writing that as a one-sided limit statement. So this is pretty easy or straightforward to integrate. We're going to now write this as a limit as a approaches 2 from the right of, let's see, that's 2 root x minus 2, evaluating this from a to 5. And we're going to then plug in those bounds of this entire statement. We've got 2. Let's plug in the 5. So that would be 5 minus root 5 minus 2 minus 2 root a minus 2. So let's continue this evaluating over here. So if we plug in that 5, that just gives us 2 root 3. Nothing about that limit is going to affect that. Now let's actually evaluate the limit of negative 2 root a minus 2 as we approach 2 from the right. Well, if we're approaching 2 from the right side, then this here is going to get closer and closer to 0. And anything times 0 is just going to be 0. So that's going to give us minus 0. And then we can then say that this integral would be 2 root 3. So this area that we have shaded in underneath this curve would be 2 root 3. We can say that this improper integral converges to 2 root 3. Okay? So that's what we do when one of our bounds is where there is a vertical asymptote. So let's do another example like that, and then I want to talk about a few different types of cases. So let's look at this first one. All right, we'll walk through this process again. So first thing we want to do is we want to establish where is our vertical asymptote. Well, since we have x minus 1 to the negative 1/3 power, so effectively that's in the denominator, x minus 1 is in the denominator, I should say. Well, the cube root of all that in the denominator. Well, let me just rewrite that. So we've got, this is this. We can then say that we have a vertical asymptote at x is equal to 1, which is where one of our bounds are. So we're going to replace that upper bound 1 and rewrite this as a one-sided limit statement. So we've got the limit as a approaches 1. Now this time, since our upper bound is where there is our vertical asymptote. We're then going to be looking at this limit as we approach from the left side. So we're then going to say 0 to a of 1 over cube root of x minus 1 dx. And let's actually integrate that now. So that would give me 3/2 x minus 1 to the 2/3 then. So we increment that from 0 to a. And now let's plug in those bounds. So that's going to give me 3/2 a minus 1 to the 2/3. And we'll actually do the limit evaluating in just a moment. Minus, we got 3/2. Let's plug in 0 now. So that's going to be -1 to the 2/3. So now we can actually evaluate that limit. So as we approach 1 from the left side, we're going to get closer and closer then to 0. And 0 raised to the 2/3, still 0, times 3/2, still 0. Then we can evaluate here, just -1 to the 2/3 times -3/2. Just want to make sure, well, so let's do times 3/2 first. I want to make sure I'm good with my signs. That should be 3/2. So we can then say that this integral, let me fix that box, I don't like that. That's even worse, but we'll just go with it, is -3/2. And this integral converges to -3/2. So we would say, yes, this does indeed converge, and it converges specifically to this value. All right. Okay, let's look at another case here. Let's look at number 3, because there's something interesting going on here. If we look at the same function, so it's still 1 over the cube root of x minus 1, but this time we'll notice that our bounds are 0 to 9, and our vertical asymptote is still at x is equal to 1. So this is our first example where we have a vertical asymptote within our bounds of integration. So what do we do here then? This effectively just means we're going to need to set up 2 limits. We're going to do 2 different one-sided limits as we approach the vertical asymptote from the left side, and then as we approach the vertical asymptote from the right side. So let me write the 2 different limits in different colors so we can see this. So we're going to say, all right, the limit as a approaches 1, because that's where our vertical asymptote is, from the left side. And so this integral is going to be from 0 to a of x minus 1 to the -1/3. And actually, let me just go ahead and write that as a rational expression now while I'm at it. Okay. All right, so pause here. We're writing our first one-sided limit as we go from the lower bound to where the vertical asymptote is, which is +1. Then we're going to write our second limit statement, which is now the other one-sided limit as we go from where the vertical asymptote is, or I should say from the upper bound to where the vertical asymptote is. So this would be the limit, and we're going to use a different value for our limit. We don't want to use the same variable, a, both times. We're going to write this as b, right? This time we are looking at the limit as we come from the right side. So from this time, b, and this upper bound here being 9. Same function. Okay? So we're writing 2 different one-sided limits. We're effectively splitting up our integral into 2 parts. That dividing line being where our vertical asymptote is. We're looking at the limit as we go from 0 to the vertical asymptote, and then the second limit from the upper bound to that vertical asymptote. So once we get that, then the rest of it is just basic evaluating. So we've got the limit. Let's write this as a approaches 1, negative. We already know what the integral is. I did that in the first problem, so we're just going to write that over again. And this is from 0 to a. And you know what? Let me just keep these colors consistent for just a little bit longer. All right. And then we're going to do this now, the other part. We got the limit as b approaches 1 from the positive, same integral. And this being evaluated from b to 9. And then from here, we're just plugging in. So we already know that the limit as we approach 1 from the negative of this entire function is going to be 0 minus 3 halves. And then plus over here, we've got 3 halves times, let's see, that would be 4 minus 0. And again, that 0 comes from us finding the limit of this entire function here. As we approach 1 from the right side, everything would just be 0. And so we can just say this is negative 3 halves plus 6, which would then be 12 minus 3. That's 9 halves. So there's our integral, right? We would then say this clearly then converges to this value. Okay. All right, let me do one more example with you before I set you on your way and have you try the rest of these on your own. But let's actually look at number 4 because there's something unique about number 4 here as well. So first thing we're going to do, going through the process again, we're going to establish where our vertical asymptote is. Well, we've got a vertical asymptote at x is equal to 1. It's within our bounds of integration, which means we're going to need to set up 2 different one-sided limits. So we're going to say the limit from our lower bound to our vertical asymptote. So we're approaching from the left side, 1 over x minus 1 dx. And then we're going to set up our second one-sided limit as we approach, again, different variable, 1, our vertical asymptote, this time from the right side, from b to 3. Oh, I want to make sure I use my, oh, I did. Okay, just wanted to make sure. All right, 1 over x minus 1 dx. So let's go ahead and start evaluating here after we integrate. So the integral of 1 over x minus 1, fairly straightforward. I should write this. This is the limit as a approaches 1 from the negative. That's going to be, ooh, I'm not sure what happened here. The natural log of the absolute value x minus 1. And all of this evaluated from 0 to a. And over here, we've got the limit as we approach from the right side of the natural log of x minus 1. And this from b to 3, okay? So if I then start writing this here, I'm going to say, okay, the limit as a approaches 1 from the negative of natural log of a minus 1, and I'm just going to pause right here. Right? I'm not going to even finish evaluating because right away I'm noticing something interesting here. If I try to find the limit of this from as we approach from the left, as we approach 1 from the left, this is then going to get closer and closer. What we're saying, the limit of this is effectively looking at the natural log of 0. Well, think about that function. The natural log of 0, we know what the natural log function looks like. The natural log of 0, as we get closer and closer to the natural log of 0, this is going to shoot down towards, this here approaches negative infinity, okay? And so we are not going to get any type of finite value from this, right? The limit of something that approaches negative infinity, right? We can then say this limit does not exist. And if the limit doesn't exist, we can therefore say that this particular improper integral does not converge, it actually diverges, okay? So this is our first example of an improper integral that we've tried to evaluate analytically that does not converge. This particular one diverges, okay? So go through some of these practice problems. Hopefully this helps and makes sense. And in our next video, we will go through the last type of improper integral when we are trying to integrate specifically from negative infinity to positive infinity.